In this problem, we are given that a sinusoidal current is 0 at t is equal to negative 625 microseconds and increasing at a rate of 8,000 pi. We are also given that the maximum amplitude of our current is 20 amps. We are asked what is the frequency of IT in radians per second. To do this problem, I'm going to use this formula. It can be found in the notes linked in the description. And instead of solving for velocity, this is interchangeable with current. So we're just going to substitute I for our V's. Remember, we're solving for omega here. So we're going to be focusing on the omega inside of here. We're given the rate of change. So what we can do is change this first I to just be from I to a rate of change. In doing that, we're going to use the di dt. We're basically taking the derivative with respect to time. From this, we can take this 8,000 pi and substitute it in for this part. Now we need to take the derivative of our right side. So we're going to set this equal to, and then we know our maximum amplitude to be 20 amps. So we're just going to plug that into here. And then we are going to have a -1 because the derivative of cosine is a negative sign. So we'll have our 20 amps times a negative sign and then everything inside of it. Now, because of the chain rule, we have to look at what's in here, and this is just a omega inside of here being multiplied by our time. So we're going to have a constant omega out here. Now we have two omegas, so right now it doesn't look very friendly, but what we can do is look at this sine part. This is going to be the important part. We know a sinusoidal current is 0 at t is equal to negative 625 microseconds. And we know our sinusoidal current be like a cosine, where we have our wave like this. And this is what we're going to look at. Here, we're going to have our cosine with our wt plus the phase shift. And this is going to be set equal to 0. The reason why it's being set equal to 0 is because in this main part right here, we're using 8,000 pi. So it's increasing at a rate of 8,000 pi when our sinusoidal current is 0. And our sinusoidal current is cosine with our omega t plus the phase shift. So that's what we can say is equal to 0. Now we know cosine is equal to 0 when we have an either 90 degrees or 270 degrees. And we can see that from our graph right here. If this is the main part we're looking at, we have 1, 0, so our cosine is 0. And then when we look at this part, which is our pi over 2, we can see that our cosine is 0 and our sine is 1. So our omega t plus our phase shift needs to equal 90 degrees. However, our sinusoidal current at 0 is a negative. That's the reason why I drew this part right here. So we're going to have a negative 90 degrees. Since it's increasing, it'll be going this way, but again, because it's negative, we have to have a negative out front. Now we can just plug this into our equation. We're going to have an 8,000 pi is equal to 20 amps. And then inside of here, we're going to have our negative sign. And then everything, this part, the omega t plus phase shift, is going to be substituted out for a negative 90 degrees. And this is being multiplied by our omega. Now, the sign of negative 90 is a -1. And a negative times a negative is a positive. So if we divide this out, we're going to have 8,000 pi divided by 20 is equal to our omega. And that's going to give us approximately 1,256. So this is the answer for our first part. Now we are going to look at the period of our current source. In the notes linked below, we know the period formula is that our omega is equal to 2 pi times the frequency. And we can substitute frequency with 1 over time. So we can rewrite this as t is equal, or not time, but period. We're going to write this as period, which is uppercase T, is equal to our 2 pi divided by our omega. And we recently just found our omega to be approximately 1,256. And then we're going to get approximately 0.005 from this. And this will be in seconds. Time or period is measured in seconds. We want this in milliseconds, so we're multiplying this by 1 milli over 10 to the negative cubed. If we flip our 10 to the negative cube over, it's just going to be 10 to the cubed. So we're going to move this 3 decimal places to the right, and we're going to get approximately 5 milliseconds. So that is the answer for here. Now we need to find the phase angle in degrees. To find this, we are going to look back at this original formula right here, and we're writing it like this. So now we are going to look for our sinusoidal current at the negative 625 microseconds. If we rewrite it like this, we know we can just look at this part since we have this equation that we wrote earlier. So we're just going to look at that. In writing this, we can multiply both sides by our arc sine. In doing this, we know that we get our equation, which again we have right here, but we're just going to rewrite, that our omega time plus the phase shift equal to a negative 90 degrees. And then we can, since we're solving for only the phase angle, have our phase angle equal to the negative 90 degrees minus our omega times t. And we know our omega to be 1256.636. This is being multiplied by our t, which we know to be 600 or negative 625 times 10 to the negative 6 for microseconds. And since we need to convert this to degrees, this is going to be multiplied by 180 degrees over our pi radians. And after we carefully plug this into a calculator, we are going to get that our phase angle is equal to approximately negative 45 degrees. And this will be the answer for our last part. And that is how you would go about solving this problem. If you want more introduction to circuit analysis, there's a playlist and notes in the description below covering this entire course.